Bismillahirrahmanirrahim. Today we are going to do sequential logic. So before we do sequential logic, let us review what is combinational logic. So logical circuits for digital systems can be divided into either combinational logic or sequential logic. So combinational logic, as you guys are already familiar with, it consists of input variables and the logic gates and output variables. So the block diagram is shown here. Sequential circuits, they are likely to include storage elements here. So storage elements are like memory elements, and they are combined with combinational logic. As you can see here, the input is not directly is connected to the combinational logic, and the combinational logic can store some of the data into memory elements, and these memory elements will feed back the output to the combinational circuit. So another type of sequential circuit is known as synchronous or clocked sequential circuit. So synchronous circuits means that the circuit is synchronized to a clock. So usually this type of elements involve flip-flops. So the flip-flops can store as many bits as necessary, and the flip-flop must always have a clock pulse, right? So these flip-flops will be used to time or to synchronize the combinational logic circuit. So the outputs will come either from the combination circuit or from the flip-flop directly. Okay, so sequential CMOS and NMOS logic circuits. The sequential logic circuits can contain one or more combination logic blocks along with the memory in a feedback loop with the logic circuit, and the next state of the machine depends on the present state and input, and the output depends on the present state of the machine and also the inputs. So there are two kinds of machines, which are the mealy and the Moore machine. So the mealy machine, the output depends only on the state of the machine, the current state. For the Moore machine, the output depends both on the present state and its current inputs. So as you can see here, these are the classification of logic circuits. So it can be combined into combinational and sequential. And for a sequential circuit, it can be divided into three: bistable, monostable, and astable. So what is bistable circuits? Bistable circuits have two stable operating points. So it can remain in either state, for example, high and low, and it can toggle. So as you can see, for example, in latches, flip-flops, memory cells, they can toggle between 0 and 1 or high and low. Monostable circuits have only one stable operating point, and even if they are temporarily perturbed to the opposite state, they will return in time to their stable operating point. So it is basically this monostable circuit only have one stable operating point. Astable circuits have no stable operating point, and they oscillate between several states. And this is example of an astable circuit is the ring oscillator. So you did this in the lab. So the ring oscillator, the output is toggling like here. There is no stable state, so it is always shifting between 0 and 1. So as you can see here, these are the three basic storage cell concepts. So the first block is the flip-flop. It is a bistable component, and it is usually built by cross-coupling of logic gates. And then the difference between a flip-flop and a latch: a flip-flop is usually, it can be either level sensitive or edge sensitive. So a latch is always level sensitive storage element, and a register is edge triggered storage element. So level sensitive as long as it is either 0 or 1, it will trigger a change when the level changes from 0 to 1. Whereas 8 triggered, it is not triggered by the levels, but it is triggered by the edge. So for example, you have a clock pulse, it can be positive edge triggered or negative edge triggered. So this is the positive edge, and this is the negative edge, right? Okay, so let's look at the memory cell here. So a memory cell is comprised of two inverters which are connected back to back. That means one output of one is the input to the other, and it is and vice versa. So the memory cell or latch has two stable states where the DC voltage transfer curves cross at the V output high and V output low points. So this is the crossing point, but it also exhibits an unstable state where the VTCs cross near the V threshold switching points. Okay, so in actual physical circuits, the memory cell will never stay at the unstable point, since any small electrical noise will trigger it to one side or the other. In a numerical simulation, either in cadence or in microwave, the circuit may actually remain in unstable circuit. So this is an example. So if you have when you did the ring oscillator, for example, you had the input here is 1, and then you have a 0 output of the inverter, and the output of the next inverter, if you have a 0 input, you have a 1, and this 1 will become a 0, and this 0 will come in, and this will become a 1, this will become 1 here, and this will become a 0, and so forth. Okay, so here this is 0, and this will become a 0 here, and this will turn into a 1, 0, and a 1. So it will always toggle from one input to the other. So this only happens when there is an odd number of inverters. Okay, but if you have a even number of inverters, so for example, this is 1, 0, 1, 1, this one goes back into the input and it repeats itself. So this is known as the bistable circuit. This one is an astable or an unstable circuit. Alright, so this is the bistable circuit. Okay, so in an SRAM cell, you have the two inverters connecting back to back. So this is the input of this inverter, right? So, and this is the input of this inverter. Okay, so this is VI1, which is here, and so let's say we put in a 1 here, and 1 will come out as a 0 here, so this will be 0, and this 0 will be put into the second inverter, which is here, 0, which is will go here to VI2, and we will produce a 1 at this here. So this way the data is always stored inside the cell. So this memory cell will store a 1 here and will store a 0 at the output. Okay, so this is the out and this is the in. Okay, so you can either store a 1 or vice versa. So this is known as a memory cell. So you must those of you who are doing SRAM cells, so you must know how does the SRAM cell function. So it will always lock in a value and store the value in the back-to-back inverter. Okay, so this is known as cross coupling, and the memory acts as a feedback. So this is the same here. So this one is a 1, 0 and a 1, and it goes feedback. Okay, so if you have like this connection, it is the same. So here you have a 1, this will be a 0, this 0 will come into the second inverter here, and this will have a output of 1. So the Q value will be 0 and the Q bar value will be 1. Okay, so how do you write a new value? If you want to write a new value, you need to overpower the feedback loop and put in an input here, and then you can change the value of the storage cell. Okay.